So let's talk about um, AS3-10 here, the work done. Remember, we discussed the concept of work done. Work is done on an object whenever its energy, when the energy of an object changes, or to be more precise, the mechanical energy. The energy of an object can include kinetic as well as potential energy. Okay, so if the energy doesn't change, then the work is not done. Okay, that's how the work is defined in physics. It's always associated with the change in the energy. You can calculate that. Remember, we looked at the formula that the work done is the force acting on an object times the distance moved by the object. And this force is the force that's doing the work. And then we also discussed first of all, the units. The units of work done, remember, are the same as energy, because the work done can change energy. They're kind of interchangeable. So joules is the unit for work done. And we also said that if you look at the formula, the force is in newtons, the distance is in meters. So when you multiply the two, Newton meters turns out to be the unit for work, but 1 Newton meter is defined as 1 joule. So 1 joule is 1 Newton meter. Okay. And then we also discussed that there are certain instances in which you'll see that the work is, not done, and then there are other problems where work is done. Some of these problems you ask those out. So when is the work not done? Again, we considered an example when something is moving at constant speed. Something that is moving at constant speed will not do work. Okay. The other thing is that the force has to be in the direction or opposite to the direction of motion or displacement. Okay. So if you're carrying a tray, for example, in your hand, and if you're just moving it, or a book in your hand, and you're just moving at a constant speed, the net work done is 0 because your energy is not changing. Your kinetic energy is constant. It hasn't changed. Your potential energy is constant because you're not going uphill or anything like that. So in that case, the work done, net work done will be 0. But if you are pushing a table and you're pushing it, you're applying a force and moving it by a distance, if it doesn't say that it's moving at constant speed, then don't assume it is so. If something is pushing a table and causing an acceleration with a force F, then the work done would be the force that you apply multiplied by the distance moved. So the key terms are you have to look for constant speed. When something moves at constant speed, no work is done. Then no net work is done because the energy of the body is not changing. Because keep in mind that usually there's more than one force involved, and the work done by one force is counteracted by the work done by another. One force is putting energy into the system, the other is removing. So overall, we say no net work is done. Similarly, if I'm standing still, if I'm not moving at all, then doesn't matter what I'm doing, the work is not done. If I'm thinking about a problem in physics, that does not amount to work being done. If I'm standing and pushing on a wall, imagine me putting my hand against the wall and I'm pushing it. If the wall doesn't budge, if it doesn't move, then the net work done is 0. Okay? Because the kinetic and the potential energy has not changed. So in physics, the work done is always associated with a change in the energy of a body. Okay, if the energy doesn't change, then no work is done. So when something is not moving, then the work is not done. So we'll write that down too. If there is no motion, doesn't matter what you're doing. Maybe you're just lifting a weight. Maybe you're a heavyweight lifter who has a barbell in your hands and you're standing still. If you're standing still, the work is not. Net work done is 0. Because there are two forces acting. Gravity is working on that mass, pulling it down. You're pushing it up. But overall, the net effect of that is that there's no net work done. Obviously, your muscle, we're not talking about whether you're burning calories or not. We're talking about something else here. So if there's no motion, then no work is done because of the way the work is defined in physics. Okay. So we did example 1 and 2 yesterday, right? Actually, the 3 examples. If you were absent, you might want to take the notes from somebody where we did those 3 examples. I'm going to let you guys work through the rest of the worksheet. But since I'm recording this, I'll tell you what, I'll continue and I'll even do those examples. If you were absent, you can catch up. The rest of you who got it, you guys finishing this. If you were absent, since the recording didn't work, I'm just going to now show you how to, I can show you how to do that and you can follow me. Okay. So let me just do those examples quickly. First of all, it says, what's the necessary condition for a force to do work? The necessary condition is that the force is causing displacement, or force is causing the object to move a distance. Okay. How much work is done on a 2 kg block that is lifted 5 meters off the ground? Obviously, in this case, the object's potential energy has increased, right? It's lifted up. So there is work done. How do we calculate it? Well, first of all, you're given the mass, which is 2 kilograms. It's lifted by a distance of 5 meters by a pulley. We're looking for the work done. Now, work done is FD, but we have M. So how do we find the force? Well, the minimum force you need to lift this block up should be the weight, right? You should at least apply a force equal to the weight. So if you lift this block up, you have to at least apply a force which is equal to its weight. And remember, weight is mg, m times g. So what is the weight? That's 2 times 9.8. In all these problems, just use g equals 10 meters per second squared. So 2 times 10, it's a 20 Newton weight. So you have to at least apply 20 Newton force to lift it up. So that's your force. Then the work done would be FD. You write the formula, then plug it in. 20 times the distance moved, or the height to which it's lifted, is 5. So 100 joules of work is done to lift this block up. That's by how much the energy of this block will change. It will gain that much potential energy. The second one says how much work is done in carrying a 10 Newton block at a constant. The minute you see constant speed, you know that the work done is 0. No net work is done in carrying that block, because the different forces that are involved are doing, one is doing positive work, the other is doing negative work. The net work is 0. It's the net work that we're talking about here. How much work is done in accelerating a 10 Newton block over 2 meters with a force of 15 Newtons? Now, there are 2 forces given here, right? So how much work is done in accelerating a 10 Newton block? That is referring to the weight of the block. It's a 10 Newton block. Kg is mass, Newtons is weight. The distance over which it's moved is 2 meters. And the force that is causing the motion, that's the one that appears in the formula. That's 15 Newtons. So the work done would be, again, FD, F times D, which is 15 times 2, which is 30 Newtons. So you have to make a differentiation between like which force is doing the work. That's the one that goes in the formula. All right. So yesterday I showed those examples. I also recorded this. So I will make this video available to you. I'll